This is a question of JEE 1989. It is on heat thermodynamics, and from the question it seems quite daunting that it is almost of one paragraph. However, question is the concepts are quite simple and straightforward, and the formulas are very simple to remember. So I will start one by one. Let us take the example. Here we have a piston cylinder device, and it is attached with a spring. This slider can slide upward or downward, and P naught is the atmospheric pressure. When we heat this cylinder, then what is going to happen is uh, this piston will move forward and will move in upward direction. And suppose it moves to a distance delta x. So we have to calculate in this question the work done by the piston and the amount of heat that is supplied when this piston moved to a distance delta x. So if we draw the free body diagram, this is our initial state of the piston cylinder device. Initial pressure is P0. So when we draw the FBD of this piston, the forces acting are P naught A, this is the atmospheric pressure. P naught is atmospheric pressure. And if the mass of piston is given, then it is mg. If it is negligible, we can leave it. So these two forces are balanced by the internal pressure of the gas, which is P1 into P1. So the force is P1 into A. From equilibrium equation, initially this piston is at rest, so it is P1 into A equals to mg plus P naught into A. If we simplify it, then initial pressure P1 is P naught plus mg into A. If the weight of this piston is negligible, then initial pressure will be equals to atmospheric pressure. That is quite obvious. So in the final state, when the piston has moved to a distance delta x, we can again draw a free body diagram of this piston. This is the atmospheric pressure which is acting on it, P naught into A. This is the weight of the piston, which is mg. And now there will be a spring force, that is K delta x. These forces will be balanced by the pressure of the gas, that is P2 into A. And from equilibrium equation, we have P2 into A equals to mg plus P naught into A plus K delta x. When we simplify it, P2 equals to P naught plus mg plus K delta x into A. This is the final pressure. Or for any intermediate pressure, we can write it as P equals to P naught plus mg by A. And here what I have done, I have multiplied A by in numerator and denominator. So this expression is important because what we see here is that the pressure P is proportional, directly proportional, because these two quantities are constant. Uh, Similarly, K by A square is also constant. So in fact, pressure is something like a linear relation of volume. So we can write it as P equals to A plus BV, where A and B are constant. So for these types of question where pressure is linearly proportional to volume, we can see that rather than solving those complex kinetic potential energy of spring or to calculate work done by spring, we can solve it from the graph. And here you can see that from the graph, work done pressure is linearly proportional to volume. This is the linear portion, and it increases from P1 to P2. Initial volume is V1 and final volume is V2. So work done is area under the PV curve, which is this portion, this portion. So area of this trapezoid is sum of parallel sides into height. One of the parallel side is this one, this is your P1. Another parallel side is this one, this is your P2. So sum of parallel sides will be P1 plus P2, and the area is P1 plus P2 divided by 2 into delta V. Here it is a mistake, sum of parallel side into height divided by 2. Sorry for the mistake. So this is our work done. So as if the question is asked only about the work done, it is very simple and it is straightforward, that is P mean into delta V, where P mean is P1 plus P2 divided by 2. This can be calculated very easily. V is, so delta V is the change in volume, that is A delta X. So finally we have work done equals to P mean into delta V. If we have to calculate the energy stored in the spring, so this triangular portion is the energy stored in the spring. So we can calculate this area. This area is half base into height, and height is delta P. This height is P2 minus P1, and this is V2 minus V1. So it is delta P into delta V divided by 2. This is the energy stored in the spring if it is asked in the question. Now the next part is we have to calculate the change in internal energy of the gas, so that we can finally calculate the amount of heat transferred. So delta U is NCV T2 minus T1, or we can substitute CV as R upon gamma minus 1. So it is NR gamma minus 1 T2 minus T1. Now from ideal gas equation we know that P1 V1 equals to NR T1 and P2 V2 equals to NR T2, and when we subtract it, the volume V2 is V1 plus delta V. This will be used for calculation, so I have written here. So when we substitute P2 V2 from P1 V1, we obtain P2 V2 minus P1 V1 is NR T2 minus T1. Now substituting the value of V2 as V1 plus delta V, we obtain this P2 V2 minus P1 V1 as P2 V2 minus P2 delta V minus P1 V1. So rearranging, we obtain P2 V1 minus P1 V1 plus P2 delta V, and this finally changes to P2 minus P1 into V1 plus P2 delta V. So we can write it as delta P into V1 plus delta V into P2, and that equals to NR T2 minus T1 from this one. So finally the change in internal energy, which is NR upon gamma minus 1 T2 minus T1, and when we substitute the value of NR T2 minus T1, we obtain delta U as delta P into V1 plus delta V into P2 divided by gamma minus 1. So this value is our change in internal energy. So work done was P mean into delta V, and here change in internal energy is delta P into V1 plus delta V into P2 divided by gamma minus 1. So finally our formula work done is P mean into delta V, delta U is delta P into V1 plus delta V into P2 divided by gamma minus 1, and the amount of heat supplied will be change in internal energy plus work done, that equals to Q equals to delta P into V1 plus delta V into P2 divided by gamma minus 1 plus P mean into delta V. For the given question, these are the numerical values that were given. P1, P2, delta V and V1 were given. Based on this, we can calculate work done, that is P mean into delta V. P mean is here is 3 by 2 into 10 raised to power 5, and this was delta V. So work done is 1200 joule. Similarly, we can calculate delta U, that is delta P into V1. Substituting these formulas, we finally get delta U as 600 joule. So total heat supplied is work done, that is 120 joule, plus the change in internal energy, that is 600 joule. So this is our final answer. Amount of heat supplied is 720 joule. If we have to calculate the final temperature, we can use the gas law, P1 V1 by T1 equals to P2 V2 by T2. From there we can calculate the final temperature. Thank you.